I've had a few folks ask me about the Skydiver problem that is the computer project that's due next Wednesday. So I wanted to talk about it just a little bit to give you an idea what you should be expecting as you look at it. So the idea is we have a Skydiver far above the Earth's surface, and she's going to be falling, and we want to basically plot her position and eventually velocity as functions of time. So in part A, things are pretty easy. You could do the calculation analytically. I just ask you to say you've got a constant force. So you have your Skydiver, mg down is your force, and so you can just plug that in and do the calculation analytically if you want to. I would like you to do this step computationally and go through and iterate with time, as I'll show you in just a second here, just kind of some pseudocode to get an idea of what you want to be doing. So this is just to basically to practice, to make sure that your analytical simple expression matches what you get if you actually step through this thing over time. And then in part B, we said, well, we know that this little g here is only valid if you're right on the surface of the Earth. And in reality, so say this is the surface of the Earth here, in reality our Skydiver is way up here at some height above Earth, y. And so gravity is no longer equal to just mg, and it also isn't a constant. It depends on how high above the Earth she is. If she's up here, it's going to be, the gravitational force is going to be weaker than down here. So still just that one gravitational force, but here the force of gravity is a function of y. And so here we actually need to go back to Newton's law of gravitation. So the force of gravity is g times her mass times the mass of the Earth divided by the radius squared. In this case, the radius is just the distance from the center of the Earth, down here, to the Earth that I've drawn here, plus her height, y here. So I can plug that in. So this is the radius of the Earth plus her altitude above the Earth's surface, y, and then that thing gets squared. Sorry about the light right there, it's kind of hard to see. So we can plug this in for the force. And we're going to be stepping time, but it's important to realize this thing doesn't explicitly depend on time. It depends on her height, her altitude. And that's going to depend on time. So this y is a y of t. So at each time step, we're going to plug in her altitude in order to calculate the force. And ultimately, what we're going to need is her acceleration, so you can cancel out her mass. So you'll notice I didn't in the problem. Oh, I did give you her mass. I did give you her mass. All right, and then so you can do that second part now, just including the height-dependent force. And so this is different from what we talked about in class, just doing linear or quadratic air resistance. In this case, we have so that would be a velocity-dependent force. This is a position-dependent force. So this is, again, something that you couldn't solve analytically. All right, and then in the third case, we have both our height-dependent gravitational force. So if we were to draw a free body diagram here, we have our gravitational force that depends on position. And then we also have a drag force. So let's see this thing, we'll call this F drag. And this includes a little bit more subtlety than what we have done in class. So this is a position of both velocity and the height. So the idea is you only have drag when you have air molecules around you. And her original height of about 100 kilometers is much higher than the height of the atmosphere. So that only goes up to about 10 kilometers. And so you'd expect to have some sort of exponential decay of the Earth's atmosphere. And so at first the drag force isn't going to affect her at all. And then as she gets closer and closer to the Earth, it's going to kick in. So I tried to give you a form for what that drag force would look like. So that drag force, we said, is going to be, so I'll let you figure out the sign, but it's that k term times m times v. And then we also need to include this decaying exponential. So we had e to the minus y divided by some length scale here. But that was our, 10 kilometers we said it was in the problem. Yeah. So this is our drag force, this is our gravitational force, and we can plug them both in there and work through the problem that way. Okay, so for each of these three parts, what I'm asking you to do is to do an iterative calculation where you take a time step and then calculate the different mechanical properties. So to set it up, you're going to need to pick some dt. Should be some small number, maybe 0.1, maybe 0.01, 0.001. Again, as we said in class, you want to pick some number and then try smaller time steps dt to see if that changes your answer. So this is in seconds. So I would start with something like 0.1, just as a ballpark guess. See if you need to make it smaller or not. Put in your original height, your original velocity, and set your time marker to be equal to 0. And then here's the bulk of what you're doing in your program. So at each time step, you're going to say, time is equal to my last time plus dt. Now, at this new time, I'm going to calculate my force. That force depends on, so in part A, it's just going to be a constant. But in parts B and then C, it's going to depend on both my altitude, my height above the Earth's surface, and the velocity. I can calculate the acceleration by dividing that force by the mass. I can calculate the velocity, as we talked about in class on the second day of this idea of time stepping through these equations. My original velocity from the last time step plus the acceleration I just calculated times my time step dt. And the position, same idea, my last position plus the velocity times the time step dt. You'll have to be a little bit careful in here in terms of defining your coordinate system appropriately so that your velocity is either positive going down or negative going down, and choose your signs accordingly. You should be able to tell pretty easily if you're getting answers that are, your altitude is increasing, for example. And so then the idea is that you would loop this until y is less than 0. Because when y is less than 0, she's hit the ground safely, and your program is done. So once y goes less than 0, then you can escape your loop and you've done your work.